So good morning everyone. Let's come back to the natural language processing class. So today we will discuss information theory and its application to NLP. So we talk about this in three sections. The first one introduces entropy and the maximum entropy principle. The second one talks about several measures about two distributions of the same random variable. And the third section talks about the correlation between different random variables. Okay. So let's begin with the first one, entropy. So before we talk about entropy, we need to first learn what is information. So information theory started in the 1950s. So when people work on communication and deciphering, so formally information is something that we use to resolve ambiguities. So for example, if I tell you there will be no final exam this term, okay, so I tell you some information. When I inform you that tomorrow the weather is going to be warmer, I give you some information. So by resolving ambiguity, I mean, before I tell you that there will be no final exam, there is a chance that you will have final exam. There is a chance you won't have it. Right? So when I give you the piece of information, you resolve the ambiguity by fixing the possibility to only one of the choices. This is resolving ambiguity. So how do we measure information? The information measure is deeply connected to binary encoding. So, for example, if I have two choices, right, whether you have the final exam or you don't have the final exam, and I resolve this binary ambiguity, well, you can use one bit to encode the knowledge. Where 0 means you have the final exam, 1 means you don't have the final exam. Right? So I can send you the information in 1 bit of message. Right? I send you 0, you mean you know that there will be final exam. Okay. So how about when there are 4 equally possible outcomes? For example, you randomly draw a card, okay, from a deck of cards. You know that the number of cards in 4 suits are equal, okay? So when I draw 1 card from a deck, okay, without the jokers, the chance of having spade or diamond, okay, is 1/4. Okay. So when I tell you that I got a spade card, okay, the ambiguity that is resolved is a choice out of 4, right? So I can encode this choice using 2 bits. Okay. Maybe I send you 0/0 for spade, 0/1 for heart, 1/0 for club, and 1/1 for diamond. Okay. So you can use log2 for 2 bits to encode such information. Alright. So we can understand that the uncertainty or the number of equal choices, okay, that we resolve equals the information that I give you, and the equation is log2 of the number. Right. So let's look at more examples. So if you draw 1 card, okay, from a deck of cards without jokers, you know that 13 times 4 equals 52 cards. Okay. If I draw 1 and I tell you that the card that I drew was spade ace, okay, I resolve ambiguity from 52 equal choices to 1. So the amount of information I gave you was log 252. Okay. But if I tell you I drew a spade card, okay, essentially the ambiguity that we resolved was from 52 equal choices to 13 equal choices, because there are 13 spade cards, right? So the amount of information I gave you was log 252 minus log 213, okay, which is equal to 2 bits, as we calculated before. But now we took a different perspective, right? We took a perspective from individual cards. What about I tell you that I drew an ace card, okay? So this time, the original uncertainty was log 252. And after I tell you the information, the ambiguity was log 4, because there are 4 ace cards, right? So you can calculate that the amount of information I gave you is log 252 minus log 24, which is equal to log 213 bits. Right? Okay. So that is about equal choices. Every outcome has equal possibility. What about unequal choices? What if you have prior knowledge that it's more likely that we will have an exam this term? So if you knew beforehand that we're more likely to have exam, and I tell you that we won't have final exam, then I definitely give you more than 1 bit of information. How do we quantify that? Okay, so let's think about drawing a ball from a box. Okay, let's imagine there are red balls and green balls in the box. If we have 5 balls in total, and out of which 3 are red, okay? If I tell you that I have a red card, a red ball, then what happens is the original ambiguity was log 2, 5, right? 3 red balls, 2 blue balls. Information the log 2. So this is when I tell you that what I drew is a red ball. What if I tell you that the ball I drew is a green ball? Okay. Originally there are 5 uncertainty choices, right? And after I tell you I drew a green ball, the uncertainty became 2. So the amount of information I gave you is log 2, 5 over log 2, 2. So log 2, 5 over 2. So you can see that when I tell you that the ball is green, I give you more information than when I tell you the ball is red. Why? Because there were more red balls in the box than green balls. Right? So the amount of information I give you in general is log 2, 1 over the probability of your outcome. Right? So the probability of having a red ball is 3 over 5. And the amount of information I gave you was log 2, 1 over this probability. So the more likely, okay, the original choice was, the less information I give you when I tell you that this happens. This is understandable, right? So if you know that most likely at the end of the term you will have a final exam, okay? And I tell you that you will have a final exam, so I don't tell you too much. On the reverse, if I tell you you won't have a final exam, then I tell you much information. So in general, when the probability of one outcome, R, of a random event E, okay, is PR, then the amount of information of receiving this outcome is log 2, 1 over PR, or minus log 2 PR. Okay? So this is in general when there are unequal choices, not necessarily equal choices. Okay. You know, one random event can have a lot of different possible outcomes, right? So one random variable can have a lot of different possible values. Okay? So, information, as we discussed just now, measures the possibility or the number of bits we need, okay, for encoding one outcome or one value of a random variable. What about the random variable as a whole? Okay, if we have a random variable and we know the probability of each outcome, okay, can we have an estimation of the expected number of bits, okay, we use to encode all different outcomes? Right? Why is this significant? Because suppose that I constantly tell you the outcome of a random event, okay? I need to constantly tell you one outcome after another. So I send you a long bit string, okay, of outcomes. For example, weather forecast for the next day, day after day. So in the long run, the total amount of bits I use to encode these outcomes, okay, is the cost of sending such information to you, right? And in the long run, this total number of bits depends on the expected number of bits I use to encode any outcome, right? Okay, so this is a measure in the random variable level, okay? Rather than the random variable value level. This is an overall understanding. Okay. What is this expectation? This expectation is called entropy, or information entropy. It measures the number of bits I need for encoding a random variable in the long run. Okay. How do I denote it? We already know that for each outcome, right, the number of bits is minus log 2 PR. Alright. So let's do a mathematical expectation of all the outcomes. Okay. We do a sum. I equals 1 to n. N is the number of outcomes, right? So PRI, the probability of this particular outcome, times minus log 2 PRI, the number of bits I need to encode this outcome. Right. So this is the expectation, and it determines the number of bits I need in the long run for encoding this random event. Okay. So for more frequent outcomes, okay, the weight is higher, and the weight is the probability. Okay. In other words, entropy is the mathematical expectation of encoding an arbitrary outcome of a random event. Alright, so now we know entropy. So, will the entropy be different if the distribution is different? That's the next question, okay? Now suppose we toss a coin, okay? I toss a coin, and I tell you the outcome of each toss, alright? So, if the coin is fair, you know that every time I tell you the result, I need one bit of information, right? So in the long run, the expectation will be 1 bit. The entropy will be 1. Okay. Now the question is, what if my coin is unfair? What if most of the time you see head rather than tail? Okay? If this is true, will I have to spend more bits to tell you the outcome or less bits? This is my question. Okay. So whether the coin is fair or not reflects whether my distribution is uniform or not, right? It turns out that if my distribution is non-uniform, okay, if the coin is unfair, then I need less bits to encode the information in the long run. How is this true? Let me give you a more sophisticated example. Let's suppose that we throw a dice, okay, we throw a casino dice. You know there are 6 faces for the dice, right? 1, 2, 3, 4, 5, 6. Right. If the dice is fair, how many bits do we need for encoding the outcome? Log 2, 6, right? So 6 equal outcomes. Log 2, 6. Unfortunately, this is not an integer, right? So we have to take the ceiling, which is log 2, 8, 3 bits, right? So if the dice is fair, we need 3 bits to encode 6 numbers. What are the 3 bits? Okay, intuitive to understand. 0, 0, 0, or maybe not 0, 0, 0. Let's say 0, 0, 1 for 1. 0, 1, 0 for 2. 0, 1, 1 for 3. 1, 0, 0 for 4. 1, 0, 1 for 5. 1, 1, 0 for 6. Okay? And this is the ASCII encoding for integers, if you're a computer science student. Anyway, we use the 3 bits to encode 6 numbers. You know there's 0, 0, 0 and 1, 1, 1, which we didn't use because 3 bits can encode 8 equal trices, right? But we only have 6. Now, what if my dice is unfair? What if most of the time I get 1? Okay, let's suppose that 95% of the time we get the number 1, okay? And 1% of the time we get 2, 3, and 6 respectively, okay? That adds up to 1, right? Alright, so if that is the case, we don't have to take the pain of encoding every number using 3 bits. We can just encode maybe 1 using 1 bit, 0, okay? And then I add a 1 to the beginning of all the other numbers. I use 1, 0, 1, 0 to encode 2, okay? 1, 0, 1, 1 to encode 3, etc. 1, 1, 1, 0 to encode 6, okay? So when I do this, I send you the bit string. You know, whenever you see a 0, you take 1 bit off, and you know that you got a 1, okay? Whenever you see 1, you take 4 bits off, okay, and you interpret whether it's 2 or 6 according to the other 3 bits, right? So you can encode the 6 numbers in this way. But what do I care? I care about how many bits I send in total, right, in the expectation in the long run. So 95% of the time I use 1 bit, right? 95% of the time I use 1 bit. And 1% of the time, no, 5% of the time I use 4 bits, right? So what does it mean? So it's 0.95 plus 0.04, right? I end up using 0.99 bits, less than 1 bit, to send you each outcome, much less than 3 bits, right? I end up using less than 1 bit, about 1 bit, to send you 1 outcome in the long run, okay? Alright. No, more than, less than 1 bit. So it means that the more unfair, okay, the dice is, the more bit saving I am, okay? Because you have one very expected result, you can use 1 bit to encode this result most of the time. All right. So we can look at the entropy of tossing coin again in this slide. Okay. So the x-axis shows the probability of head. Okay. The y-axis shows the entropy. As you can see, when the head probability is close to either 0 or 1, okay, this coin is very unfair, right? And the number of bits or the entropy is close to 0. Close to 0. And when the coin becomes closer to a fair coin, the probability becomes closer to 0.5. I have the largest entropy. Okay, largest entropy. Which means, okay, the more uniform the distribution is, the larger the entropy is. Okay, this is the intuition. It applies to any probability distribution. All right. Okay. So now we have learned information and entropy. Okay. How do we use this as a principle of training probabilistic models? This is the second question. For this question, we need to mention an ancient philosopher called Occam. So, Occam said, entities should not be multiplied beyond necessity. What does it mean? It means that before you know anything about something, okay, don't make assumptions on it. Right? So when I translate that to a random variable, okay, it means if you don't know some prior knowledge about this random variable, okay, let's not assume any prior knowledge, or let's assume that the distribution is as uniform as possible. Okay, so this principle is now known as the maximum entropy principle. Maximum entropy principle. For example, when you don't know anything about a coin, okay, it's the safest to assume that it's a fair coin, okay, without assuming that it's unfair. This is called the maximum entropy principle. Now we could use the maximum entropy principle to train a model, to train a probabilistic model. Let's do a simple parameterization, okay? Let's suppose that we are modeling a categorical random variable, or a random variable with multiple choices, such as drawing a random word from the vocabulary, or a casino dice, right? So there are capital M outcomes of this random event. And let's denote the random event as E, and each outcome as R1, R2, until Rn. And let's assume that our model parameters, right, are the probabilities of each outcome. So this is our parameterization, right? We use PRI, PR1, PR2 until PRm as our model parameters. And you have learned that there are only m-1 independent model parameters because they sum up to 1. What is the problem? What is the entropy of this this distribution? You know, it's the sum of I equals 1 to m p of Ri times minus log 2 p Ri. Okay. So this is our entropy. Okay. This is the model parameter, our PRI, right? And this is the entropy of our model. Okay? So we've got an equation. And according to the maximum entropy principle, we can maximize this whole equation, okay, by adjusting these model parameters. This is what we can do, right? So how do we do that? We take the derivative of this thing, okay? So this is objective function. We take the derivative of this thing with respect to each PRI, right? Can we do that? Let's say the objective function f is equal to this thing. So we take the derivative of f with respect to PRI, okay? Without losing generality, let's just assume it's Ri. How do we do that? It's equal to, so this is a product, right? We use the derivative rule for product. It's this one, the derivative times this one. So minus log 2 Pi, okay? And the derivative of this one and times this one, right? So this is positive 1, okay? And we set that equals 0. When we do this, we are modeling 6 free model parameters, right? But in the end, we have only 5, right? So we need to add a constraint to this optimization problem. How do we add a constraint? We say we want to maximize the entropy subject to the fact, right? Such that sum I P Ri is equal to 1, right? We have this constraint, right? The sum of all model parameters need to equal to 1. We didn't factor that in, right? So if we directly maximize this thing, we cannot guarantee that there are only 5 free model parameters, right? So this is a constraint optimization problem. How do we solve this problem? We look at a numerical solution. So the next slide shows the solution, the Lagrangian method, right? The Lagrangian method. So the Lagrangian method solves a conditioned optimization problem into an unconditioned optimization problem. So by adding a Lagrangian multiplier, so we say we want to maximize this original objective function, right? But under these constraints, so we can look at, I add a lambda, which is a Lagrangian multiplier. So sum of I, P, Ri, minus 1, okay? This is our constraint. We want the constraint to be true, right? So we want this thing to be 0 in the final objective. And we add that with a Lagrangian multiplier to the original objective. And so this is Lagrangian equation. We maximize this thing instead. Maximize this thing instead. So when I further take this derivative, we got a lambda in the equation. And we set this instead to 0. We set this instead to 0. And when you maximize this Lagrangian equation, you realize log 2 PRI is equal to 1 plus lambda for all outcomes Ri. Right? And because they're all equal, and you further solve this equation, and you realize PRI, for every Ri is equal to 1 over 6. Okay, so we train our model. So our model parameters is PRI, right? Oh, no, sorry, not 1 over 6, but 1 over M, capital M. But M is 6 for casting casino dice, right? So we parameterize the model by taking each outcome as a model parameter, like the probability of every outcome as a model parameter. And we maximize the entropy of the whole model to find the parameter values and we found a uniform distribution. We found a uniform distribution. So that's a very simple model. For let's look at a more practical example. Let's look at a feature-based model. Okay, let's look at a feature-based model. We don't parameterize our model by directly using the outcome probabilities as model parameters. But now, suppose that our model calculates the probability of an output given an input. Okay. So to this end, we need to first look at how to define a conditional entropy, or the entropy of a conditional probability. So this time, the modeling target is no longer px, where x is the value of a particular random variable, capital X. But we care about py given x. Okay? So our modeling target is a conditional probability. So this y can be the class label if you do classification, right? So we care about such a model. And this model is parameterized by feature vectors, like what we learned in week 3 and week 4. Okay. But we don't know how this feature vector is calculated into this py of x. We want to first look at how do you calculate the entropy of this thing. Okay. How do we calculate the entropy of this thing? Well, if you're given an x, if you're given an input, okay, the entropy of the output, according to what we observed earlier, okay, is like this. We need to sum up all possible values of y. Okay, y is a random variable. Let's take lower y as. So we sum it up. Log minus log 2 py given x is the number of bits we need to use, right, for encoding every possible value. And we do the mathematical expectation. So this is the number of bits we need to encode every y given an x. But we don't know x yet, right? We don't know what is x. X is our input. So in the end, we have to do an expectation of x as well. So we need to do an expectation over x, right? Sum of all possible input, right? The input probability times this output encoding. What does it equal to? It equals to, let's take the sign here. So negative sum x, sum y, px, py given x, log 2 py given x. Right? And what is this thing? In chapter 2, we learned that px times py given x is equal to the joint probability, pxy, right? So we derived something. So we should show it in the slide. So sum x, sum y, minus pxy log 2 py given x. So this is called conditional entropy. Okay? It's the number of bits we need for encoding an outcome in the conditional probability, py given x. Alright, the derivation process is shown in the next slide. This is what I calculated just now. Okay. So great. Now we know conditional entropy. We can apply the maximum entropy principle for deriving a model, okay, a discriminative model. Okay, let's do that. So the model is defined over a set of data, xi, yi, where we have capital N instances, right? Now, I said that our model uses features over x and y. You remember feature vector, right? We discussed it in week 3, right? So we extract a lot of different patterns. For example, word and class label pair, okay? What if the document contains kick, okay? And the class label is sport. So this is one feature instance, right? What if the document contains loan and the class label finance? Okay, this is another feature instance. We assemble all the feature instances together and we get a long vector. Okay, that's the feature vector for representing the input and output pair. Right. So let's denote each feature instance as f1, f2 until fm. Okay. So this contributes to the feature vector. And in general, each feature instance is defined as fi x and y. Fi x and y. So given any pair of input and output x, y, we can map it into a long feature vector. Okay. All right. Next, the modeling target is py given x. Okay. And we have a set of data. So we know an empirical distribution of x, px. How do we calculate px? We say p tilde x. Why p tilde x? I use tilde for denoting empirical distribution or relative frequency. Right? So when we assume that our data set contains all different kinds of inputs, different kinds of documents, okay, it's intuitive to believe that the data set is like this. Right? So and then the empirical distribution of any input is 1 over d. So the number of documents, okay, 1 over the number of documents. So this is what we have. Now, we need to have some constraints for deriving our model. We don't know our model yet. We don't know how do we parameterize py given x yet. Okay. What we know is we have a feature vector. Okay. What do we want? What do we want the model to behave in the long run? We want the feature vector, right? We predict, okay, for any expected input and output pair, okay, expected x and y, okay, is equal to the feature vector that we see over the data set. This is the assumption, okay. To put it another way, so if you draw, okay, any instance, a document and a class label, okay, from the data set, okay, and in the feature vector we have maybe the 2001 element is loan and finance, right? Loan and finance, okay. So if I draw any document class pair from the document, okay, then we get an expectation from the empirical set, right? So the chance of having the loan and finance feature instance may be 0.005, okay? 5 out of 1,000 chances you see this feature instance 5, okay? I can observe that from the data set, right? By calculating relative frequency, okay? How many times did I see this feature instance in one? Right? So this is okay, what's the probability of seeing this feature? 0.005. Okay. Loan with finance. Cool. And I want this chance to be exactly the same as what's the chance of drawing this feature instance out of any input-output pair, okay, as calculated by the model. Model expectation. I want the model expectation of a feature instance to be equal to the empirical observation of a feature instance, okay, relative frequency. How do you denote that? So the expectation of a feature, fi xy, okay, is equal to the empirical expectation of the relative frequency of fi xy. So this is the constraint, okay? We want to derive the model parameterization by making some assumption about features, okay? In other words, I want the features we calculate from the data set to represent, okay, the truth calculated by the model. That's the only constraint we have, okay? So now, how do we calculate the model expectation of a feature? Okay. How do I calculate the model expectation of a feature? Let's look at slide 23. Okay. The model expectation of a feature can be calculated in the first equation. You know the expectation of feature is sum of all possible x, sum of all possible y, right? Pxy, the joint probability, times the feature. I can say, in general form, any expectation, okay, any expectation is equal to sum of all possible x, sum of all possible y, p of xy, the joint probability, times the feature, the number of features you see in this xy pair. Okay, this is a general form, right? General form. When it comes to our modeling target is py given x, right? So when we try to calculate this joint probability, we have to extract py given x as something to calculate using the model. Okay. Now you know this joint probability is equal to p of x times py given x. Okay. So this is the expectation of the feature. Okay. I just extracted px out. All right. Now we have the model here, which we want to calculate. What about this px, the prior probability of x? We don't know it, right? We don't know which document is more likely. But we know the relative frequency in the data set. Let's use p tilde x to approximate px. This is 1 over d, right? So if there are no identical inputs in the data set, then every input has equal probability. So that's 1 over d. So this derives the first equation in the slide. So this is the model expectation of the feature. Okay. Now the second equation in the slide is the empirical expectation of the feature. That's very easy. That's very easy. Why? Because you just calculate the number of features and you divide that by the total number of instances in the data set. Okay? How do I do the pseudocode is like this. I go over every instance in the data set. Okay? And I accumulate the number of times I see this feature in this current instance, okay? And I go through all the instances, I do a cumulative sum of this feature. This is the number of times I see this feature in the data set. And then what I do, I divide this number by the total number of instances in the data set, right? So that is the number of times I expect to see the feature in any instance in the data set. The total occurrences of the feature divided by the total number of documents. That is the second equation. Relative frequency. Okay. What I want is, I want this expectation to be calculated by the model, okay, to be equal to that relative frequency. That's a constraint. That's a constraint we want. Under this constraint, I want to derive the parameterization of the model. Okay? So let's do the same. By using the same principle as what we did just now. Okay? We want to calculate the Lagrangian equation and we want to maximize it. What's the Lagrangian equation? The Lagrangian equation should contain two components, right? The first component is the conditional entropy, okay? This is the training using the maximum entropy principle. The second component is the constraint or the Lagrangian term, okay? What is the constraint? We have a feature constraint. And we also have a probability constraint. Given any x, the total probability of all possible output is 1. Let's first write the first term. Sum x, sum y, right? Px, py given x, log 2, py given x. So this is the first term, the conditional entropy. Now here, we need to use the empirical observation, right, to replace the expectation of x, because we only saw our training data. Okay. Now the second term, we need to add a Lagrangian multiplier. Let's say, for all the features we are the same, sum I equal to 1 to m. Okay? We have lambda I, the Lagrangian for this feature. How about I write it separately? Plus sum I, okay? Lambda I. What do we want? We want sum x, px, sum y, py given x, times this fi, x and y, right? To be equal to what? To be equal to sum x, sum y, p tilde xy times fi xy. Again, we need to replace this px with p tilde x. So this is what I explained to you just now. This is our assumption, right? If you draw a random instance out of the wild as you calculate the expectation of the feature by the model, it should be the same as if you draw a random instance from your data set. Okay, the expectation of you seeing the feature. We have a third constraint. What is that constraint? The constraint is sum x, sum y. Okay, we need to add a Lagrangian multiplier here. Lambda. Let's say this is lambda m plus 1, because we had m Lagrangian multipliers already, right? So m plus 1, but this Lagrangian multiplier should depend on x. Sum x for every x. Okay? Okay, let's write it this way. For every x, sum x, lambda m plus 1 x, sum y, p y given x minus 1 should equal to 0. So we must make our model a probabilistic model, right? So that it gives us a probability distribution. Right. Good. So this is the Lagrangian equation. Okay? Maximum entropy principle. Model assumption. We need to find out what is py given x. Okay? So here, what should we do? This is a function. We need to find a function to maximize this. So let's apply some functional analysis, right? So we need to change this function derive the optimal point. Now let's assume that in order to do this, okay, let's look at any point in the function, any value of the function, by fixing the pair x and y and taking the derivative. This is what we could do. Okay, now suppose we change the function. Okay, we change the function, but at any point of the input, okay, given x and y, this function becomes a number, right? So we can treat it as a number and take the derivative in order to find this. Without generality, to fix an xy for all different x and y, okay, the derivative is the same. And we can maximize this function. So let's just take the derivative over this pxy at any point xy. What is equal to? So for this part, okay, so it's p of x. Let me know if my derivation is wrong, okay? There's a minus sign. We take the derivative of this thing. Oh, we saw that before, right? We saw that before. So this one, the conclusion is that there's a log 2 and log e issue. The conclusion is that it turns out that this log 2 and log e only affects the whole equation by a constant. So let's assume we can ignore log 2 or log e. Okay. So this is something times log something. So we use the derivative rule. So first, let's take the derivative with respect to this part, and we end up with log 2, or let's just say log, okay, p y given x. And then we fix this thing and take the derivative with respect to that thing, right? So it's plus 1. Okay, so this is p tilde x. So we finalize the derivative for this part. For this part, let's take the derivative. Here we have the term. Here we don't have the random variable, right? So we only care about this one. So this one is plus some I, okay? So lambda I, p tilde x. So fi xy. So this is the derivative over this term, okay? Tell me if I did it wrong, okay? So for this one, we still have the random variable, right? If I take the derivative of this one, by assuming we already have x and y, we get lambda n plus 1x. Okay? Then we set this one to 0, right? We want to set this one to 0. So this one is log p y given x, right? Log p y given x. Okay? So let's derive this 1 over p x lambda over p x. Okay? When this is equal to 0, we can derive this. So this one is on one side of the equation. The other side of the equation is 1 over p tilde x plus some I, lambda I fi xy plus lambda n plus 1x over p tilde x. But this is constant. This is constant, right? So these are all constant. So in the end, we get something as we show in slide 25. Okay. So Py given x should be proportional to what? So from this one, we know Py given x should be proportional to a constant times e to the power of some I lambda I fi xy. Right? So I don't have somewhere to write it, but we have it on the slide. Okay. If Py given x is proportional to e to the power of some I lambda I fi, okay, and we know that for all possible y values, okay, the sum of Py given x is 1. So we end up with having this equation. We end up with having the equation in the middle here. So Py given x is normalized, okay? Its numerator is what we have in here. So e to the power of some I lambda I fi xy. And the denominator is the sum of all possible y, this exponential term, right? Sum of all possible y. So we got this equation. This equation is very familiar to you. What is this? This is a softmax function, right? So in other words, we use a maximum entropy principle to derive a parameterization of the model that is exactly the log linear model. Okay? So we found some deep connection between a mathematical principle and the log linear model we learned in week 4. Okay? But we're not finished yet. Why? Because we're yet uncertain about the Lagrangian multipliers. We've only derived a model form by fixing this Py given x. We can still optimize Lagrangian multipliers in order to maximize this lambda function. Okay? But what is this? What is the process of optimizing Lagrangian multipliers? Now, these lambda are actually free parameters in the maximum entropy model or the log linear model, right? So for every instance of the feature, you have a weight on the feature, which is uncertain. You optimize these weights in order to maximize the entropy of the model. And you immediately realize this is a model training process. Right? The derivation process we just had was a parameterization process. And if you further find the values of lambda, okay, in order to maximize this Lagrangian, it's the model training process. Okay? Given the parameterization, we train our model so that every feature has a weight, right? Then we can calculate the probability of every output given an input. Okay. So this is equivalent to the training objective of the log linear model. Okay. So it exactly coincides with the maximum likelihood estimation principle, because what you're maximizing is the probability of the training instances. Okay? All right. Okay. So thus far, we discussed entropy and the maximum entropy principle, and we drew connection between this principle and the log linear model. Okay. Due to that reason, log linear models are often called maximum entropy models in natural language processing. Okay. So when you see a maximum entropy model, you realize if this is parameterized by a feature vector, that's the log linear model. Right. And by that, we finish the first section. Let's move on to the second section. Let's spend some time to discuss um, information theoretic measures of different probability distributions regarding the same random variable. Okay. So let me begin the introduction by revisiting what we had last week. So you remember last week we learned in order to optimize the model, we essentially minimize some empirical risk, right? No matter whether it is the log linear model or perceptron or SVM, these models all minimize some empirical risk as shown in the slide. The risk is 1 over n, where n is the number of instances, logs, okay, as calculated by your model. And if it's a linear model, then it's theta dot phi. Okay. So this is what we are trying to minimize. And for a probabilistic model, okay, this loss, this risk, can be quantified by the difference between a model probability QD and empirical probability P tilde D. What is this empirical probability? As we know, if every input D, okay, is different, then this PD should be 1 over n. Okay. But how do you quantify the difference between two probability distributions? Okay. So let me give you one example. Let's say we just use log 2 PD minus log 2 QD as a difference, okay, between the two probability distributions. And in the end, the empirical risk is written as, okay, the sum of 1 over n, okay, log 2 PD minus log 2 QD. Okay, this is one very reasonable way, right, to derive the difference or the loss according to the model probability and the empirical probability in the data. Okay. So, and then further, what is that 1 over n? This 1 over n is exactly PD, the empirical distribution. And in the end, the risk or the loss function we just defined is something like what is in the green box, right? The sum of I equals to 1 to n. PD log to PD over QD. This thing, okay? Or we write it as the expectation, okay? The expectation over PD, okay? Log 2 PD over QD. Okay. So that is what we're trying to optimize, and we got something, okay? The expectation over P, okay? Log 2 P over Q. Something in this shape. And this thing is called KL divergence, okay, in general. KL divergence in general. This P is not necessarily an empirical distribution, and this Q is not necessarily a model distribution, but you can regard them as two different distributions concerning the same random variable, okay? For any two distributions, we can measure the KL divergence. Okay. And this KL divergence is non-symmetric. So KLPQ is different from KLQP. Okay. And we also have a fact that the KL divergence of two model distributions is always greater or equal to 0. It is 0 only and if only the two distributions are identical. Okay. Why is that so? We will see a bit later. But this is about KL divergence. We now know the shape, okay? KL divergence is a form of loss function, right? It's a form of loss function, empirical loss function, by taking the difference between the log 2 of empirical distribution and the model distribution as the loss, okay? And we got the KL divergence. Let's take a closer look at this divergence. What does it do? So next slide, KLPQ is equal to the sum, okay, of all data instances, PD, bracket log 2p minus log 2q. Okay? It's also equal to the sum of PD log 2pd minus PD log 2qd. Okay? Now the first term is a constant, you know. It's completely empirical distribution, PD log 2pd. We don't have to care about it. What is the second term? Okay? The second term is minus, okay, sum I is E1 to n, okay, 1 over n log 2qd. What is this? This is the average of model probabilities over the whole training data, right? The average of log probabilities over the whole training data. Negative log probability, what is it? Negative log likelihood, right? Negative log likelihood. Because QD is the model distribution. It's the distribution of D calculated by the model. Alright? So when we try to minimize the KL divergence of P and Q, we effectively minimize the negative log likelihood of Q. Okay, so it means this risk function, okay, we just defined, is equivalent to MLE. Minimizing the negative log likelihood is equal to maximizing the log likelihood. Alright, so when we minimize KL divergence, we maximize likelihood. Okay. But, okay, next, let's look at this negative log likelihood again. What is it? Okay. It's 1 over n, right? Negative log 2q, okay? But if you regard 1 over n as p, you know, it's negative expectation over p, log 2 1 over q. What does it mean? What does it mean? So, okay, I won't write it on a whiteboard. So it's negative expectation over p, okay, log 2 QE. What does it mean? You know, negative of log 2 QE is information, right? It's a sort of encoding mechanism. It's how many bits of information we need for encoding the outcome of a random variable, right? According to a probability distribution Q, okay? Suppose, okay, we have a distribution Q, and minus log 2Q of a particular random variable value is the number of bits we need for encoding this, okay? When we calculated entropy, we used Q itself for calculating the expectation, okay? Sum, okay, all possible outcomes, Q of R, log 2QR, right? Now what we did is we used a different distribution P to do the expectation. We say sum of all possible outcome R, right? PR minus log 2 QR. Okay. This means that we use a different distribution to do a weighted sum of a particular encoding scheme Q. We call this a cross entropy. Cross entropy. Okay. It's a sort of entropy, but the expectation probability is different from the encoding probability. We name it HPQ. Okay. I use P to do the expectation of Q encoding. Okay. So what does it measure? It measures the difference between P and Q. Alright. It turns out that if you use Q for doing the expectation, you got the most economic encoding. Just as what we showed on the whiteboard, right? If you have an encoding scheme, if you have a distribution, and you draw the encoding, you draw the expectation of the encoding according to the distribution itself, you save the number of bits. Okay? You're the most economic. You use the least number of bits to encode something in expectation. Now you use a different probability distribution to do the expectation. The cross entropy turns out, okay, to be larger, okay, than the entropy of Q itself. Okay, you can prove that. You can prove that. I won't have time to give you a proof. So HPQ is always greater than HQ if P is different from Q. This is the conclusion. And let's take this conclusion back to the KL divergence. Okay, and KL divergence is equal to HPQ minus HP in the end. Okay, so that explains why KL divergence is always greater or equal to 0. Okay, all right. So in summary, we looked at a loss. Okay, we looked at a loss, which is a KL divergence loss, and we analyzed the loss. Minimizing this loss is equal to maximizing the log likelihood. Okay, and the log likelihood term is also known as the cross entropy between the model distribution and the empirical distribution. As a result, from now on, we can call the MLE objective a cross entropy loss objective. They're the same. They're the same. There are only two different views of the same thing. One from a probability perspective, one from a information theoretic view. Okay, they're the same. Right. Now I introduced the cross entropy loss and also the KL divergence definition. They can be used as training objectives, but they can also be used as regularizers or evaluation metrics. Okay. Next, something related to cross entropy. Okay. It's called perplexity. Now, perplexity can be defined, okay, on one single distribution. It's as simple as 2 to the power of entropy. 2 to the power of entropy. You know, entropy measures the expected number of bits, right, to encode an outcome for random variable. So 2 to the power of entropy can intuitively be understood as how many equal choices you have if the whole random variable is treated as a uniform distribution. Okay, despite that it's not equal. This is called perplexity. Okay. Suppose you have a dice, okay? Suppose you have a dice. When the dice is fair, HP will be equal to log to 6. And 2 to the power of HP will be equal to 6. The number of equal, right, choices is 6. The perplexity for an equal dice is 6. The perplexity for a fair coin is 2. The perplexity of any fair uniform distribution of categorical random variables is the number of choices. Okay. But if the dice is unfair, okay, you know the perplexity is smaller than log to 6. Okay. You translate this entropy to perplexity. Okay. You got some number smaller than 6. For an unfair dice, okay, the perplexity is smaller than 6. So it translates to, okay, a fair dice. The number of faces is smaller than 6. Okay? So you're using a fair dice as a view to look at your unfair dice. How many equal choices do you have? Okay. The smaller the number, the less perplexed you are. The less perplexity it is. Okay? If you have a very, very unfair dice, it can shrink to the perplexity of a fair coin. Okay, the perplexity can be as small as 2, or even smaller. Okay. That's how you translate entropy back into perplexity. But you had cross entropy, right? Which is a measure of how different two distributions are. You can translate that cross entropy into perplexity too. Okay? If the cross entropy is the measure of model and empirical distributions, then your perplexity is called model perplexity. Okay? You can use the model perplexity to evaluate a model. In chapter 2, we learned n-gram language models, but we never learned how to evaluate these models, because unlike classification problems, you don't have an absolute correct answer, right? You can say a lot of different sentences. You can say a lot of different next words given the previous K words. Okay? So there's no one absolute answer. In the end, how can you measure how good your model is? You can use cross-entropy or model perplexity to this end. You just run your n-gram language model over a set of real human written sentences, okay? And you calculate the information theoretic measure, the model perplexity of these sentences. And that's a measure. Or you can calculate a per word perplexity. You just run your model through the sentences by calculating the model probability of every word, okay? And you translate that to a cross-entropy measure or a model perplexity measure, okay? The lower this number is, the better your model is, okay? At the time, for n-gram language models, it could be 200 something, okay? But now, with the best neural models, this one can be close to 10 or even smaller than 10, okay? You have an idea. The vocabulary is very large, right? The English vocabulary, maybe you have 10,000 words or more. But when it translates to model perplexity, you see less than 10 equal words. Okay. So this gives you an intuition how ununiformly distributed languages are. Okay. Now, mutual information. It is a measure, okay, of two different probability distributions, okay, of two different random variables. To understand this, let's take a look at the conditional entropy again, okay. We've learned hy given x, okay, just now. And we know hy is the unconditional entropy. What about we take the difference between hy and hy given x? Through computation, we don't have time to go into detail. The difference is equal to the sum of all possible x and y, the joint probability times log 2, joint probability divided by the product of individual probability. This thing. The first thing you see about it is that it's symmetric, right? It's symmetric. Okay? So it means that hy minus hy given x is equal to hx minus hx given y. Okay? It tells you the correlation between two random variables. What is it? We define that as the mutual information. Okay? And it turns out that this mutual information measures the probabilistic dependencies between two random variables. Why? Because if you look at the term in the log 2, okay, the joint distribution over the individual distributions, right? We know by definition, if pxy is equal to px times py, then the two random variables are independent. And in this case, the mutual information is 0. Okay? Otherwise, okay, the entropy y, hy, will be different from the entropy y given x. In other words, so if you know something, this something is x, then the entropy of y will change. Okay, before you know x or after you know x. Okay? This thing is the mutual information. If x is irrelevant to y, then ixy is equal to 0. Otherwise, when they are conditionally dependent, then after knowing x, your entropy will change. Your entropy will change. Okay? And how does entropy change? It can become smaller if X can positively inform Y, but even larger if X can negatively inform Y. Okay. So I draw you the correlation between entropy, conditional entropy, and mutual information. You can see the correlation here, which translates to the equation I just showed you. Okay. But the next thing is, mutual information is a random variable level measure. Okay. But there's a corresponding random variable value level measure. To entropy, that measure is information, log 2 px. To mutual information, that measure is called pointwise mutual information. Okay. If we are given two particular values of random variables, x and y, then pointwise mutual information is log 2 pxy over px times py. Okay. The expectation of pointwise mutual information is mutual information, random variable level. Okay. So this is easy to understand. So mutual information is two pointwise mutual information as entropy is to information. Okay, you can understand it this way. As a result, information is also called a self-information. Self-information. Okay. Now, pointwise mutual information can be used directly in NLP. I'll quickly go through several examples. First, look at slide 50. What is log 2 pxy over pxpy? Okay. So if x and y often co-occurs rather than occurring individually, right? This pointwise mutual information p and y will be large, right? Otherwise, if both x and y are frequent, but they don't frequently co-occur, this one will be small, right? If they co-occur as they individually occur, they are conditionally independent, this one will be 0. Okay. So PMI is 0 if they're independent. Positive if they're positively dependent. Negative if they're negatively dependent. Okay. As a result, we can use PMI to mine out those strongly correlated random variables. Okay. So first example, sentiment lexicon. So we know some good words and bad words, good and bad, okay? We can calculate any word if it co-occurs with good more than it co-occurs with any other word, okay? By drawing the PMI between a word and a seed word, we can guess whether this word has to be a positive word or not. So this is the first use. You can read more details, okay, by reading the textbook. Next, collocation. What is collocation? If two words strongly co-occur together as a meaning, for example, Mr. President versus Mr. Executive, or high temperature versus big temperature, right? So there are collocations. So you can use PMI between two words to mine out collocations automatically. So this is the second use. Third use, you can mine out the correlation between features and your output class labels to see whether some features are indicative to the class label, right? You can use PMI between features and class labels to filter out features to make your high dimensional space lower dimensional. This is the third use. You can read more details. The fourth use, you can use PMI to represent words. This is the last thing I want to discuss, okay? How do you represent a word? We learn how to represent a document, right? So by counting the number of words in the document itself. It turns out that you can also represent words by counting words that co-occur in the neighborhood of a word, okay? This is called a distributional hypothesis of word representation. In other words, so both of these words can co-occur a lot with tail, fur, okay, head, or rat. Co-occur with the current word, you guess the meaning of the word. That's called a distributional representation of words. Okay? Compared with one hot encoding of words, where we just encode any word with a particular number, right? And that's it. And we can turn this number of one hot vector. It's a vocabulary size vector, where the index that corresponds to this word is 1, and the index that corresponds to other words are 0. This is called one hot. Okay? Compared with one hot vector, this distributional vector can capture word similarity. If you put two words in a vector space, okay, where each word is represented by the frequency of the neighbors, then you know dog is closer than cat, than airplane, because both of these two words have more co-occurring words. When you use this distributional representation of words, you can use the absolute count over a set of data. Okay? That is a count-based vector. But you can also use the PMI between a word and other vocabulary words to represent this word. It turns out that PMI representation is better than count-based representation because it's more distributional. It avoids some frequent words co-occurring with every other word. Okay? Diluting the vector space location of word vectors. So in this sense, PMI is similar to TF-IDF. Okay? You have the probability of individual words in the denominator, similar to the document frequency in the denominator. Okay? So in this sense, TF-IDF is also information theoretically motivated. Okay. I leave more of this to you for offline reading. Okay. So that's the end of this week. We discuss some information theory. So next week we go on to discuss some latent variable methods. See you.